I am ready. So welcome again. This is the last but one lecture. Just let me check webcam and microphone. Everything is working. Yes. And we talk about climate and energy. I think it is the most interesting lecture I'm delivering with you. And it is interesting, and the reasons you know why. And just to stress the concept, I would like to say that if you go down, there is the last update date, and it's today, because today I went once again during the weekend and today through the lecture, because the last update was before than today, it was in 2024, and a lot of things changed in the past couple of years. And therefore, I made an update. I'm still using the presentation, but the presentation is not updated. So I will jump back and forth from the presentation and the lecture, which is, as I said, has been updated. So this is the presentation, and let me go back to the lecture as well. And let me start from here. So why climate and energy? First of all, because for two reasons. First of all, because energy is essential for life, and for besides than life, most less important things are human development, and our welfare depends on energy. This is well known. And a lot of things depend on energy, including water cycle. I'm just talking about energy in general, not only electricity, because very often we make confusions between electricity and energy. Electricity is the form of energy with which we most often get in touch, like today, for projecting over the screen, etc. But energy is much more. And we will clarify what is energy. And one of the form of energy, we will say, is electricity. So energy is essential for life, and this is the reason why it is important. Second reason why it is important is that for energy production, we emit a lot of emissions. We will see details. And therefore, energy production is one of the major things that are responsible for global warming. Let's say, the things that we believe are responsible for global warming. For sure, energy is responsible for CO2 emissions, and therefore, it becomes also, according to our knowledge, important for global warming. And so on the one hand, we need more energy, more and more and more, because it's essential for life, and it's essential for a good life, and for human development, also for equality is essential, because as we will see nowadays, most of the energy is used by few countries. So we want more and more countries to use energy, and this means that we need more and more energy. So on the one hand, we need more and more. On the other hand, energy production involves, among the other things, CO2 emissions. And there are also other risks related to energy production. Think of a dam for producing energy, an artificial reservoir. We have a long history of accidents that occurred for dam break, dam collapsing. And therefore, it is a very fascinating topic, and it's a challenge because we need to produce more energy, but on the other hand, we need to reduce CO2 emissions. So it is indeed one of the most important challenges nowadays for the two reasons that I said. And the implications are manifold. And one implication is conflicts. And we see today the continuous development of these conflicts, and some of them are directly motivated by energy. Most of the conflicts, I would say, are directly motivated by energy. It's not the only reason for conflicts. There are other reasons, but energy is important. And in any case, conflicts, wars have energy implications. And we see nowadays and in these weeks what's going on and what are the implications also on our everyday life, even if we are not directly involved in the conflict. We understand that, the economy is related to it, and therefore it becomes an essential challenge. And actually, energy is one of the reasons why climate change is so relevant also in the political agenda. And I'm using the term political in a positive meaning, because politics is very positive. Politics means that we plan, that we manage our societal organization. And today, very often, we refer to politics with a negative meaning, but I am referring to this term, once again, with a positive attitude. And then, once again, energy is one of the reasons why climate change ranks so high in the agenda of the politicians. So it's indeed nice that we talk about it. And our treatment will be, as usual, during this course, not really analytical. It will be it will be finalized to our understanding of the big picture. So I will not go into the details, but as you will see, there are some details that we need to discuss, which are very, very quantitative, not in mathematical terms, but in terms of definition, in terms of our understanding. It's not only an understanding that is aimed at getting an overview of the big picture. It's also an understanding that needs some quantitative definition, some rigorous definitions. And therefore, it's important that we also focus on these things that must be, in a way, stored in our memory. So first of all, what is energy? And I really would like to ask you one by one what is energy, but it will take too long, because it is interesting. If you ask people what is energy, everyone thinks that we know what is. And every one of us has an idea of energy. What is energy? So it is a word that we use during the day, maybe tens of times, like I need more energy for studying this course. I need, this approach is energetic. It means very dynamic. Or we need energy in order to run cars. We use the word many times, but if one is asked to provide a definition, it's embarrassing, because I must say, even myself, I would be embarrassed. And energy is a term that was introduced probably by Aristotle. For sure, Aristotle referred to it, but he meant to refer to the term energy in a philosophical context, because energy has also a philosophical meaning, which we ignore. We focus on the physical meaning. Okay, energy, of course, is also philosophic, because when we say it's a very energetic person, it means a very proactive person. It has to do with philosophy, but we refer to the definition of physics. So what is a proper definition? Let me go to the PowerPoint. And first, there is a consideration in my lectures about Vincenzo Balzani. I am citing Vincenzo Balzani because I think he deserves to be, he's well known, but he deserves to be better known, because he's emeritus at the University of Bologna, and he's a person who provided very important scientific contributions to chemistry and also energy production. He worked also a lot on molecular machines, something that we don't discuss, but he's a very deserving person in terms of recognition. He's 90. He's getting 90 very soon. And he said, if you want to really embarrass someone, ask what is the definition of energy. So let's refer to physics, as I said. In physics, energy is defined as the quantitative property that must be transferred to a body or a physical system to perform work or to heat. Okay, so basically we refer to a body, and we say that energy is, again, it's a property that must be given to the body in order to perform work. I say body, but we can also refer to a physical system or to heat it. Okay, and this definition is also already clarifying a basic thing. Energy means work or heat, two different forms of energy. And they are not equivalent, as we will see, because heat is a form of energy which, however, cannot be converted back. So we get heat usually when converting energy. Okay, so usually when we refer to a body or for instance, to a system like the engine of the car, we give proper fuel to produce work. So the fuel is the energy. Okay, maybe the petrol or other fuels, but the fuel is the energy. So we give the fuel to move the car. But then the engine of the car, if it is an electrical engine or it is a combustion engine, anyway, it eats up. So basically the energy serves to move the car, but the car also is heated up. This is something that we would like to avoid. We don't need to heat it up, or maybe, let's say, we don't need to heat it up to move the car, but we can't avoid it. So basically we transform the energy from the fuel in work and heat. And unfortunately, once that energy is transformed into heat, cannot be transformed anymore. So the heat is heat, and that's fine, but we cannot transform it anymore. Okay, while the car, we can the work transform back to energy. Think of recovering electricity in an electric car when you brake. So the car slows down, and some cars are equipped in order to recover the energy from the work, the movement of the car, back to electricity. So this is a back conversion. It's a further conversion of energy. And in terms of heat, then when it is heated up, the energy related to the heat cannot be converted back. Okay, good. So let me go back to the because I need to remember what I want to say, because some of the things were developed here today. Okay, so energy, water, and food are considered as primary resources, as we said. So energy is not the only thing that is essential for life. It's also water, it's also food. And once again, we already said that the Earth system is closed with only one exception, and the exception is the energy from the sun. Okay? The universe is closed, and that's it. So let's start from the universe doesn't take energy from outside of the universe. The universe is the whole body that we believe it exists. There are no other bodies out of the universe. The universe is closed, doesn't receive energy from other systems. The Earth system is closed, but with the only exception of energy from the sun. And the energy from the sun is the source of all the energy that we use. Okay? All the energy that is available to us comes from the sun. It's the only source. So let's keep it in mind. And I forgot to say one thing. What is the unit of energy? It's the joule in the international system. The joule is the energy that is transferred to an object by the work of moving it 1 meter against a force of 1 Newton. Okay, so you know that energy is measured in force times movement. This is the unit. Okay, so think of these glasses, and if I try to move them, there are opposing resistance, and these forces are, for instance, friction, etc. So let's suppose that this force is 1 Newton, okay, which by defining the force, I get independent of the shape of the glasses. I can move also the PC, okay, and it's independent. The only thing that is defined is the force against the movement. So if I move the PC, I need to make a forcing of 1 Newton with my fingers, and I move it for 1 meter, okay, in the horizontal plane. This is the joule. And then there are kilojoule, megajoule, etc. Okay, very good. So I want to give you 2 examples of how much energy is essential or it's impacting human life. Two examples, because with these two examples, you get an understanding of how much relevant is energy and how much energy we need and how much energy is involved in some events like an earthquake. It's a huge amount of energy, and this is very often outside our perception. So the examples, to produce 1 kilogram of meat, on average, requires 7 liters of oil. This is something, and by the way, 1 kilogram of meat requires like about 1,000 liters of water to be produced. So sometimes we don't perceive this relationship, these implications of activities that are essential to our life. Of course, you could say, okay, but I could avoid to eat meat, but still, to produce 1 kilogram of bean or 1 kilogram of any vegetable requires water and energy in some way. Okay, and this is not so trivial. Once I spoke with a farmer and he said, I can't believe it that I don't use 1,000 liters of water to produce 1 kilogram of meat. And I replied, okay, but did you consider everything? Because it's not just the water that you use in the farm, it's also the water that you need to produce the forage, to produce the grass, to produce, if you consider everything, there are studies about that. And indeed, we require a lot of energy and a lot of water. Another example, we may desalinate 1,000 liters of seawater. 1,000 liters is really a reduced amount. You could think of like, yeah, it's really a lot, 1,000 liters. And I would reply by saying, you don't know that, but you use every day about 150 liters of water without realizing it. If you take a shower, it's about probably 40, 50 liters. Anytime that you go to the toilet is 5 liters, maybe even more in some of the toilets, and therefore, so we may desalinate 1,000 liters of seawater with 3 liters of oil. And producing a ton of aluminium requires about 5 tons of oil. Producing a car requires about 3 tons of oil, about 25% of the energy consumed by the car in its lifetime. Because we need energy for everything. Energy production accounts for about 75% of global greenhouse gas emissions. We will see more detailed statistics. Okay. That is mainly obtained nowadays by burning only fossil fuels. We are still at about 80% of the energy that is produced by burning fossil fuels, which store the energy that in the past came from the sun. Okay, now another example. During 2000, in the fall season, and precisely between October 9 and 13, or 13, 16 October, we got a flood over the Po River. And the flood caused some minor inundations. Still, some people died. And basically, the total mechanical energy released by the rainfall mass over the land surface during this flood, relative to the mean sea level, because when you basically measure mechanical energy, you have to refer to, as you may remember from physics, to a baseline level. Okay, so if I say that these glasses have a potential energy, if I raise them, which is transformed in kinetic energy, if I release them, I don't want to release them, but if I release them, like for this here, this is the potential energy that is transformed into kinetic energy. And if I want to measure the potential energy, I can refer to the surface of the table, because I am interested in the energy that can break them, and therefore I refer to the table, because it's the height from which they fall. Otherwise, I can refer to the mean sea level. Usually, when we talk about potential energy of a body, we refer to the mean sea level. Anyway, so if I measure for the Po River flood this energy of the rainfall relative to the mean sea level, okay, let's forget about the number 0.13 exajoules, because it doesn't say much. Okay. Let me say that this amount of energy is comparable to more than 8 years of electricity consumption by New York City. Okay. and corresponds to roughly the energy of the Po River flood, roughly 2,000 times the energy released by the Hiroshima atomic bomb. So you understand two things. First, how much energy comes from the sun, because the energy of the flood comes from the sun. It is the sun who provoked the evaporation of water from the sea level to high altitudes. And therefore, this potential energy of the water was gained thanks to energy from the sun. And this is a single flood event, but imagine the amount of energy that every day comes from the sun, which is more or less the same, okay, more or less the same that the energy that came during 1 month for generating, I say 1 month, but for generating this rainfall. So you can imagine the huge amount of energy that we have at disposal from the sun. Because if a single flood may allow to support electricity consumption, cover electricity consumption of New York City, it means for a single flood, it means that probably every day we could compute it from the sun, we get an amount of energy that is more than enough. I mean, it's more than enough. This is the first implication, the first thing that we need to focus on. The second implication is you understand why floods are so risky, are so impacting to people, because it's like 2,000 times the Hiroshima bomb, but this single flood. So you understand why energy is on the one hand necessary and on the one hand available, and on the other hand, energy needs to be managed in a proper way, because otherwise it can cause disasters. Of course, what is the downside of the so large availability? The downside is that the energy, in order to be used by us, needs to be converted, because I mean the energy of the Po River flood is energy associated to water particles. We cannot use it directly to move a car or to turn on a lamp. We need to convert it, and we need to store it. This is also a huge problem, And also, we cannot, in a way, convert the full amount of energy that we receive from the sun in a way that is usable, because if it is converted to heat, very often we cannot use it anymore, or at least we cannot convert it back to other forms of energy. So either we use directly the energy that comes from the heat, or otherwise we cannot convert it back. So you understand why it's fascinating. And also, it's yeah, your question. Let me just, I wouldn't, let me from this paragraph. No, we don't need to remember, you don't need to remember anything from here, okay? For your final brief, I mean. The important thing that you need to store in your mind is the concept, the implication, the figure, like what I said, a large amount of energy, etc. But thank you for asking. If you have any doubt, and I will tell you later what you have to remember in a more explicit way. Another reason why energy is so relevant is the debate on energy transition. And here there is a figure that now I open in high resolution, okay? I am working on my website, so what I'm doing here is accessible also to you. Let's wait for it, okay? And what is energy transition? You know the word. It means that we need to pass from energy production by burning fossil fuels to energy production entirely based on renewable energy. Actually, we will define later what is renewable energy. But I can anticipate just a very short definition. Renewable energy is the energy that can be regenerated, restored in a reasonable time frame. So you use this energy, the energy can be reproduced within a reasonable time frame. Basically, if we want to be pedantic, also fossil fuels are renewable, because as they have been formed up, they can regenerate, but in geologic times. So we cannot say that they are renewable in a reasonable time frame, while solar energy, indeed, once it is used, then it can be generated again in a reasonable time frame. Okay, so basically, we want to pass to renewable energy through energy transition for obvious reasons, because, or let's say, for obvious two reasons. The first reason is that fossil fuels are going to deplete, and this is already a very good reason for making sure that we don't only rely on fossil fuels. It's sustainability. This is a reason that is basically independent on climate change, but it's already a very good reason. So even if one doesn't bother about climate change, I would say, okay, but what is your plan when fossil fuels will deplete? And this is not going to happen in a million of years. It's something that may happen in the near future, before the end of the century, maybe, that we have shortages. And also, you know, fossil fuels have implications that require, these implications, sorry, are that countries are not independent, because fossil fuels are available only in certain countries and not in other countries. And therefore, this originates the need for international trade, which is, on the one hand, fine during a peaceful period, but on the other hand, it implies a waste of resources. So it's the first reason to get rid of fossil fuels is clear. I mean, sustainability of their use. The second reason is the amount of CO2 emissions, which is very high, and therefore we want to pass to renewable energy, and we will see what are the sources of renewable energy in order to generate energy without or with a very limited amount of CO2 emissions. Actually, this is something ideal because, unfortunately, any form of energy production that you may think of has some environmental implications in terms of CO2 emissions and other environmental impact. So, for instance, I want to use hydropower. Well, okay, but building a dam and managing the dam requires CO2 emissions and also requires other risks. Okay. Okay, so energy transition. Energy transition requires a real political and socioeconomic transformation, and which we will discuss in detail. And this is, on the one hand, costly, with a high social cost. Social, I mean cost that is to be paid by citizens. And remember, any cost for human improvement must be paid by the citizens. It doesn't exist an entity that has an amount of money that covers the costs we have for human development. It's humans that have to pay on their pocket. And then we could discuss about taxation, about a more equitable ways of sharing this cost. But at the end of the story is a social cost to be paid by citizens. And unfortunately, nowadays, our system, our societal system is not very equitable. And I would say, I could also remove very and say it's not equitable. So it happens that sometimes when we make some progresses, the benefits are taken by a reduced amount of people who are not those who pay more for that. Okay, so this is something that is to be kept in mind. Is a first implication of energy transition. The second implication is the timeline. These structural changes are not easy, and the resources that are required are many, are ingent resources, are large resources. It's not easy to get them. Okay, and this transition that we would like to promote now is one of the most relevant energy transitions that the humankind has experienced. Another one is the Industrial Revolution. In the Industrial Revolution, indeed, there was a rapid change of the energy system. There was a rapid energy transition from traditional and direct burning of fuels, fossil fuels, but not mainly fossil fuels. It was burning of woods, burning of biomass, etc., to burning of coal to produce steam power. So they passed from biomass, very traditional fuels, woods, to burning coal. And this caused an intensive air pollution, CO2 emissions, but mainly air pollution. The first problem was air pollution. But once again, this energy transition that we want to promote now is one of the most relevant the humankind has experienced. Let's see if I could get the figure. This is a figure which was published in 2018 and which proposes a timeline. What is the essential message here? Before we look at some of these numbers, not to remember. What is the essential message? This prediction was too optimist. So after only 8 years, we have to recognize that these predictions were too optimistic. Let me make an example. First of all, let's look at the figure. The figure is reporting in gray information about what is our prediction of the peaks in energy demand, energy production, energy supply. So, for instance, we see here a prediction in 2032. We think that the primary energy supply, we will see what is primary energy, but basically primary energy is the energy that you obtain by using natural fuels like oil, like biomass, but I will give more details. And this is something, the details that you will have to remember, but I'll tell you, okay? So primary energy consumption, it has been predicted to peak in 2032, which means that we believe that in 2032, our production of primary energy will peak, which means that we become more efficient, we reduce the demand, and we rely more on some renewable that are not considered, as we will see, on primary energy. Let me refer to another example, which is more understandable, it's more immediate, the concept. Here you can read the 2014 coal peaked. What does it mean? It means that they believed in 2018 that the amount of coal that was used in 2014 to produce energy was the max reached by humans and then started to decrease. Why what was the reason for that? The reason was that in 2014, China prompted a very important transition, and they passed from producing energy by burning coal, and coal produces a lot of CO2 emissions, of course, to other forms of energy production. And therefore, this caused indeed a decrease in the global use of coal for producing energy, and therefore they concluded it peaked. Okay, now let me show you a link to, sorry, it's here. This is an article from The Economist in 2024, okay, published on October 2, 2024. Global coal consumption still at a record high. And here you read, okay, coal consumption is running at record levels, with 2024 similar to the previous year. And this represents a total increase of 10% on 2014 figures. So this is a prediction that was reported in the previous picture, again here, and which turned out to be wrong. And then you see in gray many other predictions. Oil peaks means production of energy through, again, burning oil peaks. Transport energy demand peaks 2026. I can tell you also this prediction, unfortunately, is not going to be true. And we start here, 19% of the energy mix is non-fossil, And this is basically the current value, okay? And here you see that they target 50% of the energy mix is non-fossil by 2050. And then here there is, in green, you see the measures, the predictions that would favor a reduction of the emissions, a reduction of the use of fossil fuels. So 2024, light EV means the electrical vehicles, EV, electrical vehicles, reach cost parity with internal combustion engine vehicles. This did not materialize. The light cars, electric cars, now have still a higher cost of purchase and maintenance with respect to internal combustion. And then you see a lot of other predictions. We don't go through all of them, where indeed we see that this target of reaching 50% of the energy mix is non-fossil. And by the way, the European Union targets to reach by 2050 decarbonization with the Green Deal. This shows that energy transition is a complicated story, and it's probably taking longer than expected. I also would like to make another consideration relating to resources and the costs of this energy transition, which is going to be higher now with respect to what will be the cost in 20 years from now, because the technology will improve. And therefore, of course, if we accelerate this transition, it's implying a social cost that is probably larger if compared with a situation where we don't accelerate the transition. And so this has implications with our discussion on climate change, because depending on the speed of climate change, depending on the evolution and development of future climate, we may also think that we could take a longer time to push for the transition, which would be a good thing, because first the cost would be diluted along a longer time, and second would be a good thing because probably the cost will be also lower. On the other hand, we have the problem of urging actions, and therefore if we say, okay, transition, it's fine if it is achieved in 200 years from today. It's difficult to motivate politicians to take a real action, because 200 years is something that goes beyond our life, the life of our kids and children, and probably also the life of our nephew, and therefore our grandchildren. Sorry, and therefore this means that the urgency of the problem, to urge people, urge ourselves to take action. It's also a philosophical motivation for targeting results by 2050. Yeah. As consequences of solar right now. As consequences of solar right now in the Swedish Arctic region. Yeah. Countries like Japan said we are going to start to use oil again for 1 year. Mm-hmm. So if this war is continue, and maybe other countries are going to use the same oil to support energy. So maybe we will reach another topic. Yes, this is very true. And another example is the war in Ukraine, and with the blockage of the use of the Russian gas for a little bit now, we are still using it, but there was a reduction anyway, has prompted several European countries to go back to coal again. And there was a speech by the Italian Prime Minister at the time, was Mario Draghi, and he said we need to go back to coal because otherwise we are not independent. And your comment is for sure true, and raises the problem of making socioeconomic predictions, because of course climate change is also related to and also energy demand. It's also related to socioeconomic prediction. Think of the emissions and emissions which are related to what you just said. And therefore it implies uncertainty. On the other hand, I understand that we have to try to fix a target, like, okay, whatever it happens, we need to have clear in mind what is a strategy, a possible strategy that we may try to implement. So we still have to have the solution ready to be applied. And I think that having an idea of the timing, even in ideal condition, is in a way useful. So for sure, these predictions did not materialize, did not prove to be true because of also social implications. But on the other hand, the concept that I would like to convey is that even in an ideal situation, I think that these predictions probably are in a way too optimistic. And the reason why, as I said, they want to accelerate is related to urging society to make something. On the other hand, if we make wrong predictions, we lose the public trust in science. So we need an approach that is very well balanced. And the first thing, in order to obtain this balance, is that young people, you know the science, and in order to be able to understand what's going on. Yeah.
As far as I understand, that was one of the most main obstacles for new energy
is a consensus. Yeah.
What was the reason to not try to widen their resources to renewable energy instead of depending on coal?
We will discuss this in more detail in what follows. So I plan to give a reply to your question a bit later on, if you don't mind. And I just would like to anticipate that there are implications, technical implications, technical challenges that are not easy to resolve. And once again, we need to make a very careful planning. But this is just an anticipation, and then I will show you later. Okay, so this figure is a prediction made for the European Union, okay, and based on the assumption that in 2050 we get full transition, full renewable energy, and this shows the source of renewable energy that would be used by selected countries. And this is important to understand what type of renewable energy we believe we can use in Europe. Of course, in other countries, the distribution will be different. The sources more or less are the same, but the distribution is different. So solar thermal, and including residence, commercial, and government rooftops, it's the light orange, okay? You see that is expected to cover a good percentage, but not really large. Okay, solar thermal means direct conversion from solar to thermal. This is due to all the systems. All the solar plants were converting the solar energy into warm water. Now we use photovoltaic plants. And these are indicated here as solar plants. And you see that there is quite a good percentage, especially in the south of Europe, but indeed solar plants are a good source. Onshore wind and offshore wind. Wind is, again, of course, in some countries more than in others, but it's, again, a very good source. And then there are other sources which include wave energy, extremely important. We can get a lot of energy from the sea, which comes from the wind, because wind is generating the waves, etc. And then geothermal, hydro, and tidal turbine energy. It looks like it's not very relevant, but on the other hand, we will see that other sources like hydropower are extremely important for other reasons. Because it's not only important the quantity that is produced, but it's also important the way it is produced. We will see why, okay? And it's also important the opportunity to store it, because we have the storage problem. Remember, energy cannot be stored with a few exceptions. You may think of batteries. Batteries is a very minor amount of energy. We can't use batteries. We can use batteries for small things like for turning the car off. But you know that if I had to run the car with energy from the battery, it's nothing, and we cannot. Or the electric cars, they do that, but they need a lot of batteries. And there are other problems, the weight of the batteries, and still a car is just a minor thing. If you have to run a complete system, you understand that battery is not a good option. And other options to store energy are, for instance, hydropower, but we will discuss it later. So the message is, it's not only important the quantity, it's also important the way it is produced. Okay, now let's go into more details and pay attention, because I mean, this figure here is just to give you a picture. What are the sources of renewable energy? We will discuss renewable energy with more details later. Okay, we are still introducing it, the topic. Okay, now forms of energy. This is something important you have to concentrate on, because this is indeed something that could be asked in a quiz. And we have many forms of energy, actually, but the main ones that are usually considered for, because they are related in a significant way to energy production, are 6: thermal, chemical, electrical, electromagnetic, and kinetic. Okay, these are the 6 forms of energy. And the nuclear, sorry, I forgot to say nuclear. The first 5 forms can be the first 5 can be transformed in both ways each other. Okay, so from thermal I can obtain chemical, and in order to transform from thermical to chemical, there are endothermic reactions, for instance. And if I want to transform thermal into electrical, then there is a thermoionic emission. You don't have to remember the single processes, just try to remember the 6 forms of energy, okay? And remember the concept that the first 5 can be transformed each other in both ways. And there is one exception, the 6th form of energy, the nuclear energy. The nuclear energy can be transformed into the other 5, but the other 5 cannot be used to generate nuclear energy. Okay. So you may say, okay, so it means that nuclear energy is not sustainable because I cannot rebuild it in the same way I cannot rebuild fossil fuels. Okay, short answer, yes, it's not sustainable, or short answer, it cannot be rebuilt, but it is actually sustainable, because from nuclear energy we can really produce a lot of energy by consuming a little amount of nucleus of fuel. Therefore, nuclear energy is indeed, in principle, not sustainable. In principle, you cannot regenerate nuclear energy, but in practice, it doesn't have really implications in terms of sustainability, because we can use several fuels, and from a limited amount of fuel, we can produce a lot of energy. Okay, and so it's important also to keep in mind this concept of conversion. So, for instance, electrical energy can be obtained by all the other forms. So if we want to generate electricity, we can generate electricity starting from thermal energy, from chemical energy, from electrical energy. Electrical energy, no. Or yes, we can also transform electricity between one form and the other. And electromagnetic, kinetic. So kinetic energy, for instance, is the transformation that we operate with hydropower production. We use running water to generate electrical energy, and also nuclear. So conversion is extremely important. You understand that this term is something that you have to well keep in mind, and energy conversion. In order to use energy, we need to convert it. And this is what we do, for instance, when burning fossil fuels, we use thermal energy to obtain other forms like kinetic energy. In fact, you see thermal energy is transformed in kinetic energy through engines. Very good. Now, we, as human, can perform all the transformation processes indicated in this figure. Okay. And this triggers an important consideration. Okay. Energy transformation is regulated by the energy conservation law, law of conservation of energy. And what is the way we state this law? It's the first principle of thermodynamics. The total energy of an isolated system remains constant. It can be converted, but still remains constant. And therefore, the expression energy production that I used so far is formally wrong. The correct terminology would be energy conversion. And remember this first principle of thermodynamics. The total energy of an isolated system, here there is a spelling error that I see here, system is singular, not plural, remains constant. Okay? And remember also the first principle of thermodynamics, because you could get a quiz question on that. Okay? It is very easy. I mean, the total energy of an isolated system is constant. Okay? And this is also something reassuring, because on the one hand, if we stop here, we may say, okay, very good. We have a very good amount of energy from the sun, which comes into the earth at any time. And therefore, if the energy into the earth remains constant, okay, of course, we could also account for a minor part of it that goes back into the space. There is some radiation, but we continuously get energy from the sun, and the net balance is positive, because the computation energy from the sun minus energy to the space is positive. The energy is conserved, so we are rich. You understand that there is something wrong here, or not wrong, something missing, because it's not reasonable that we continuously store energy in the Earth system. So it means that we need to add some more consideration. The first principle of thermodynamics is for sure correct, okay? But we need to make some further consideration. So at this stage, let's look into this box, laws of thermodynamics. Let's forget about the zero law. If two systems are each in thermal equilibrium with a third system, they are in thermal equilibrium with each other. Let's forget about it, because it's not something that is directly interesting to us. What is directly interesting is the first law of thermodynamics, energy conservation, which means that energy cannot be created or destroyed, only transferred or transformed. And here there is another consideration, which is important. The change in internal energy of a system equals heat added minus work done. Okay. Okay, very good. This means that when you use the energy, you obtain work, but also heat. It is conserved, but in this conservation, you have to sum work and heat. Okay. Second law of thermodynamics. This is very important. Okay, let's forget about the first statement, or let's postpone it. Simply put, no heat engine can convert whole heat into work. Okay, so you can convert some heat into work, but not all of it. And this is a confirmation of what we previously anticipated, that the heat can be only partly used, not all of it. So this means that if we need work, we cannot use the heat that was produced for energy conversion. So if we transform thermal energy by burning fossil fuels into work in an engine, into kinetic energy in an engine, the engine of the car, the heat that is produced, yes, to some extent can be retransformed into work, but not all of it, for sure, not all of it. And what can we do with the remaining heat? Nothing. Or at least we cannot use it to produce work. And we can use it to maybe to heat an house. And so we use, for instance, geothermal energy, and to produce, we use the heat from the thermal energy to heat the house, but we cannot convert it back to work. This means that there is something that we lose, because we lose work. Okay, and this is why, in a way, the energy that we get from the sun needs to be continuously updated. We need to continuously take more energy in the Earth system, because there is the heat that we cannot use to produce work. And for many uses, human uses, indeed, we need work. Okay. Second law of thermodynamics, the formal way of defining it. The total entropy of an isolated system always increases or remains constant. It never decreases. What is entropy? Entropy is a measure of disorder. It's a measure of uncertainty. And basically, entropy, when entropy increases, we have less capability to produce work. So there is energy that we cannot use anymore to produce work. And therefore, entropy is something that when we convert energy increases. Think of the universe, not the Earth system. And we know that there is a conclusion from these two laws that the entropy of the universe tends to a max. So it's continuously increasing. What does this mean? It means that if we think of the Earth, that's fine. We have energy that comes from the sun that replaces the work that we lose, the capability to make work that we lose. But if we think to the universe, there is no replenishment. So the universe as a whole has the usable part of the energy that is decreasing. And therefore, this means that it will come to an end one day, which is something that is obvious. We know that the sun will come to an end one day, and therefore, I mean, it's not something that is unlimited, the energy from the sun. It is unlimited in the span of the human life and more than the human life. I mean, also in geological terms, it's unlimited. We don't have evidence that it's decreasing, but we know for sure that it will finish, because it's burning fuels, and therefore It's burning fuels, not only burning fuels, it's also using nuclear energy. Nuclear energy that is going to deplete. And being nuclear energy, it will last for a long time, but it will get to an end. Probably life over the Earth will finish before the sun finishes its life, because for many reasons. And like on Mars, probably there was life and it was gone. Also on the Earth, when the nucleus will stop moving, therefore generating the magnetic field, it will come to an end. But indeed, it is true that the total energy of the universe, the usable energy, is going to finish. This is something that is not directly related with our problem, just to gain a better understanding, okay? So here, conversion implies a degradation of energy, namely, energy is conserved after transformation, but its capacity to produce work decreases, okay? And okay, this does not mean that the total quantity of energy present in the universe is decreasing, rather its ability to work is. This is what I just said. And the thermodynamic function assessing the degree of energy dispersion is called entropy, okay? And try to get an understanding of what entropy means. It's important, it's just a statistical measure, but here I'm not going into details because it's not our purpose, but for your skills, try to get an understanding. Okay, so we then took into consideration a possible classification of energy, which splits the energy forms into 6 forms. And it is particularly useful to understand the way it can be converted into forms that typically are used by us. And we use the kinetic energy, we use the electromagnetic energy. And for instance, when we use the light bulb incandescent light lamps, we made a transformation from thermal to electromagnetic, and we also generate electrical energy for many reasons. And the first reason why we need electricity is that we can transport it. Okay? And because not all the energy forms can be easily transported, electrical energy has this very important behavior. So first classification, 6 forms, try to remember them. This is just my first message. Second classification, and this is also very important to understand energy and the use we make of it. Primary energy versus secondary energy. So what is primary energy? And primary energy consists of unconverted or original fuels. Let's look at the example because it makes it more understandable. Primary energy, crude oil, hard coal, natural gas liquids, natural gas. Nuclear energy is a primary energy, okay? Waste is a primary energy, okay? Because we can use waste to obtain energy or better, we can convert energy associated to wastes to other forms of energy, like we can convert the energy associated to crude oil. And then primary energy also includes some renewable. And by the way, so far, nuclear energy, you can think of it as a renewable energy for the reasons we already discussed, okay? And wind energy is a primary energy, geothermal energy. The energy related to biomass, like woods, okay? And hydroelectricity is a primary energy, it's considered to be. And wave and tidal energy, etc. With hydroelectricity, we mean hydropower. This is not very correct to write hydroelectricity because electricity is already a secondary energy. It's a conversion, okay? But if you interpret here hydroelectricity as hydropower, then it is correct, okay? Wave and tidal energy. And then we can transform this primary energy, but if there is a transformation, then it's a secondary energy. And so basically petroleum products is considered to be a secondary energy. Like, for instance, the petrol that we put into the car or the oil that we put into the car is derived from crude oil. It's already a transformation, which unfortunately implies some losses. Okay, and manufactured solid fuels, there are many examples of them, and manufactured gases, many examples. And this is secondary energy. Electricity and heat is secondary energy. And biofuels, it's a secondary energy. Don't make confusion between biomass and biofuels. Biomass is the mass, is the biologic mass of course, the biologic mass that in this case, in this context, can be converted into energy. And they have different way of different efficiencies, but in principle, any biomass can be converted into energy. Biofuels are typically fuels, so after transformation, that are derived from biologic products. Like, I don't remember, there are some vegetable oils, I don't remember the name in English. In Italian, we say olio di colza, oil of colza, and colza is vegetable, and which produces an oil that can be very efficiently used as a fuel. It is a biofuel. Okay, so keep in mind these examples and the definition of primary and secondary energy, because you will get some questions like a list of energy forms, like petroleum products and manufactured solid fuels are what? Primary energy, secondary energy, a mix of the two. This is a typical quiz question that you may get. Okay, so we learned two classifications. Okay, the first one in the 6 categories we mentioned earlier, the second one between primary and secondary. The second one is particularly important for your understanding of scientific contribution, for understanding the science. And what is the implication here? The implication here is that there is a transformation, a conversion in between, which implies some reduction of the capability to produce work. Okay, now, global energy budget and greenhouse gases emission. This is extremely interesting. And this graph here, which I got from our World in Data, I checked recently, it's still the same. Because this was downloaded in 2024, so it's basically unchanged, and shows the global greenhouse gas emissions by sector. Why it's important here? It's important for the more than 70% emissions related to energy production, which makes clear why energy production, energy is relevant to climate change. It's clear, okay? And of course, it's not only transportation energy. Don't make the mistakes of assuming that it's energy related to running the car, because running the car is something that is very visible, it's very frequent, the attribution of the most of the CO2 emissions to the usage of cars and planes. Actually, if you look at transport overall, and with road transport, road transport is 12% of global emissions. So it is significant, but it's not really a huge contribution. And if you look at aviation, which is something that is attributed a big responsibility, is only 2% of the global CO2 emissions. So, I mean, it's significant, but it's not really important from a quantitative point of view. Maybe it's important from a conceptual point of view, like let's try to, in a way, not to explode in the usage of aviation, but on the other hand, it's not very important. And its energy use in industry is what matters more in terms of emissions related to energy production, because it covers one-fourth of the global CO2 emissions, one-third of the emissions related to energy production. And then there are other statistics that are indeed interesting, like the importance of agriculture, forestry, and land use. It's almost 20%. So it's turning to a green economy. It's not automatically implying a reduction of CO2 emissions. And that's it. Another important consideration, which I already anticipated, it's the contribution of different sources of energy to energy production, to global energy balance. Global means world energy balance. The fossil fuels are responsible for 81%. Coal is at 27%, oil 32%, gas 22%. And now we have, and then we have the renewable. The renewable is about 19%, including nuclear. But actually, if you look at the renewable, there are some of them who make some emissions, like woods, burning of woods, burning wood, and also biomass. Burning biomass implies emissions. So this, it's not automatic that renewable means no emissions, as I anticipated a little bit earlier. Renewable means something that can be renewed, but it's not no emissions. Okay. Still, I mean, hydro, in terms of emissions, is more. It's an advantage with respect to burning fossil fuels. If we look at the emissions per unit of joule that is generated, it's fossil fuels are probably fossil fuels, and burning woods are those that are more less efficient, let's say. And here you can see that hydro accounts for only 2.5% of the global energy balance. Again, one may say, this is very reduced, but let's postpone the discussion on hydro, because hydro actually it's extremely important, and I will explain to you later why. Nuclear is 5%. Actually, it was planned to become much larger, but then we had the two important accidents that I will discuss later, which caused a decrease of our usage of nuclear energy. Solar panels and wind turbines actually, at the present time, cover only 1% of world energy. In terms of electricity, is a bit larger, but I mean, their contribution to the 20% of renewables is very low. And therefore, this is a bit conflicting with the predictions that I showed to you earlier, predictions that were assuming that for 2050 in Europe, solar energy would contribute to a significant extent. This implies that a big change is still needed. And second, this implies that we need to check whether this big change is indeed doable, it's feasible. Okay, good. Now let's look at the demands. Now I am presenting some statistics that allows you to get a picture. And the picture is that, I mean, we need a lot of energy, and there are emissions related to it, and we need to promote a transition, but the current situation in terms of energy balance is what you see here. And here it's the current situation of current primary energy use by fuel type. Why primary energy? Because we are referring to fuels here. So fuels is primary energy. And here you see the situation and the progress from 1990 to 2035. And so there is an increase of the usage of energy production, which is, of course, understandable and obvious. But still, you see that up to now, there are no big changes into the trends. So we didn't succeed much we succeeded in improving our production by renewables, but still, given that the demand is increasing, also the production by burning coal, by using natural gas, by burning liquid fuels, fossil liquid fuels, it's increasing. Okay, and here you see the total energy production by countries. And I don't see the legend here. The legend is in the caption. So yellow, if I well remember, is China. Let's see. Yellow is China. Brown is Russia. And light blue is Africa. Blue is United States. Green is Europe. And the dark green is Central and South America. And the decrease in Europe is also due to the fact that Europe is started to rely more on the importation of energy because we wanted to decrease the coal production and the nuclear production. And therefore, Europe is relying on importing energy. And dark green is Central and South Africa. And dark green is Central and South America. So you see that what is here is relevant is on the one hand the pattern for Europe, on the other hand the pattern for China production, which is something that we know it's due to the development of China in the past 25 years, and Europe that is declining, as I already said. Okay. Now, this is classification or an estimation of the global energy use by these four categories provided by the International Energy Agency in 2017. So residential use is 21%, transportation 29%, industry 29%, other 21%. And here you see for the global energy consumption from 20 to 2020, each year is a bar, and the category of fuels used for energy productions are listed along the horizontal axis. What you can see here is that indeed coal peaked in 2014, and then there was a decrease, but then started again to increase. And oil, there was a decrease after the pandemics, but just for a minor duration, and the overall trend is increasing. Natural gas as well, and it's increasing more because it has been promoted a larger use of natural gas after, of course, the concern on the burning of fossil fuels, but natural gas is not renewable. Nuclear is almost constant. We will discuss it later because, as I said, there were some accidents, one in the United States and another one in Europe, that discouraged the development of nuclear energy. Hydro is almost constant, and the reason is that hydro doesn't offer an unlimited availability, and hydro was exploited in the Western world, was exploited during the years from 1920 to 1960-70, and then in the Western world, basically all the opportunities were depleted. They went off of available sites. In China, there has been an increase of hydropower production, which justifies, in a way, the small trend, the slight trend, but still, it's not very large. And then there is wind plus solar, from which you can see that there has been an increasing trend, but still, the amount of energy that we can take from it is very limited. Okay, total world energy consumption by source. This doesn't say much more of what I already said in other figures. Fossil fuels 80%. These are independent sources, but still you see that the picture is coherent. And renewable is, at that time in 2010, it was around 17%. Now we are at 21 at the global level. What is interesting is to see the zoom here between the different kind of renewables. And here you see that there is hydropower that is contributing 3%. Yes, this is what we already know. And biomass heat that is covering the larger part of renewables. And biomass heat is anyway something that is producing some CO2, not really many emissions, but still there are emissions. Okay, now let's now look at renewable energy in detail, and I want to make an introduction before we make the break. And so first, of course, renewable energy is the key to decarbonization, and we already defined what is renewable energy, so it can be replenished along the human time scale, and therefore does not include fossil fuels. And here you can see that the progress of renewable energy capacity from, I think it's from the past, I think it starts from 2000. And there was a large improvement, a significant improvement after 2020, basically, around after 2015, after the Kyoto Protocol and after the Paris Agreement, there was an improvement. And for the last years, you see a detail on the individual contributions to renewable energy capacity, which, as I said, it's increased, and now we are at about 21%. But if we look at electricity, almost 1/3 is produced now by renewable energy, which is a good result because electricity is anyway something that is very important. The problem is environmental impact that we will discuss after the break. Before the break, I just wanted to show you that most of renewable electricity energy is generated by hydropower. So if we look at the total electricity, hydropower contributes 16%. In terms of renewable electricity, so electricity generated by renewable sources, it's about half due to hydropower. So this means that in front of only 3% of global energy generated by hydropower, when we refer to electricity only, it's 16–17%. I think the number is not reported here. And if we refer to renewable electricity, it becomes almost half. So this highlights, given that electricity is anyway, despite electricity being a fraction of the total energy that we need, is a fraction that is very important for obvious reasons, including artificial intelligence, etc. So we see that given the importance of electricity, this means that hydropower matters more than 3% that is the estimated contribution to global energy production. So this is one first reason to say that hydropower is important. It covers a significant fraction of electricity. And you see that also nuclear covers a significant fraction of electricity, and it's indeed significant. But the main message that I want to deliver is precisely about hydropower. And let me also say why the second reason why it's important. or the second reason out of three. The second reason is its flexibility. We cannot control the generation of solar energy. We can control the generation of electricity by hydropower. What do I mean with control? We cannot basically, we don't have a switch to generate solar energy. Solar energy is generated when they decide to generate it. They, I mean nature, okay? So solar energy is generated when there is sun, when there are no clouds. Wind energy is generated when there is wind, and we cannot switch the wind off or on. Hydropower, we can switch off or on. So hydropower is essential, and I stress it, essential to compensate our inability to manage the amount of energy that is produced by other renewables, which cannot be directly controlled. So we can rely on solar energy if we integrate our use of solar energy with the use of a resource that can compensate for the lack of solar energy. The same for wind energy. So without hydropower, even if it covers a relatively small amount, we couldn't use completely solar energy. So we should rely on other forms that can be regulated. Burning fossil fuels is the same thing. We can regulate it. We can decide when to burn it. So keep also in mind this fact, given that energy cannot be stored in a large amount, can only be stored in a limited amount, we need some flexible energy sources to compensate for the lack of flexibility of some renewable energy sources. This is extremely important, and hydropower is really something that gives us this possibility without implying a lot of CO2 emission. It's quite unique, the role of hydropower. There are some emissions for building the dams, but of course, in terms of emissions, hydropower is much more efficient than burning fossil fuels. And this is a second reason for stressing the importance of hydropower. And the third reason is the opportunity to store it, but we will discuss this later. So let's meet again at 3:05. So hydropower, the third reason for making it so important is storage. Storage can be obtained with hydropower by storing water. Of course, this is related to the opportunity to make its usage very flexible. Storage is indeed used, for instance, also when there is plenty of energy available from solar and wind power that cannot be stored, the energy in excess can be used to pump back water into the artificial reservoirs. This is usually done, indeed. It is usually used, the excess of energy through hydropower, to the excess of energy by solar and wind sources that cannot be regulated is used to regenerate hydropower by pumping back the water into the reservoirs. So in a way, accelerating the hydrological cycle. This is another reason for stressing the importance of hydropower, because it can compensate the other sources of renewable in two ways. The first way is by using indeed hydro generation only when it's needed, and the second way is by pumping water back into the reservoirs when there is plenty of energy available. And this makes hydropower at the end of the story so important. And this is why also recently countries in Asia are promoting the usage of hydropower. If you look at the list of the world's largest dams, indeed, it's in Wikipedia, list of the world's largest dams. So first of all, the largest in the world is the Three Gorges Dam that was recently built. But if you look at the list here of, and you make the list in order by reservoir volumes, okay, and actually the Three Gorges is the largest in terms of, let me see, of hydropower potential, installed capacity. Or yeah, I think it's the largest in terms of installed capacity, and it's in terms of reservoir volume is the 1, 2, 3, 4, 5, 6th one. But you see that there are many recent dams here completed in recently, especially in countries with low GDP and countries like China that underwent a significant development. And if you scroll down the list, you see that in the East, there has been a lot of the dams recently built. Very good. And this is an analogous picture related to wind energy generation, which can be understood by the wind power density potential. It's a map that you can find in the site of the World Bank group. Of course, where there is more wind, there is more potential. What is the problem of hydropower? What is the problem of wind energy? And what is the problem of the solar energy? So hydropower, the problem is related to the environmental impact of the artificial reservoirs. And of course, the necessity of relying on available sites, which are not so widespread and only in certain countries. The problem with the wind power is, again, environmental impact due to noise and due to the change in the landscape visual. The noise is particularly relevant because I'm not sure if you tried to get close to a wind power turbine, but it's really very noisy. and also the usage of the land. And this is a common problem with the solar energy. Solar energy, which is related to the global horizontal irradiation. So you can see here the zones of the globe where there is more potential for solar energy. What is the problem? The problem is the usage of the land. Indeed, this is recognized as a significant problem because recently there's been a lot of conversion from agricultural land to solar farms because, of course, they are more, they produce more income with respect to agriculture, especially in specific countries. And the usage of the land is also causing an impact on the distribution of the runoff because underneath the solar plants, there is limited infiltration, and therefore there is also an implication on groundwater, and there is also the problem of the visual. Of course, solar panels are very good in terms of when they are displaced on the roof of the houses, but when they use the land, indeed, it's a potential problem. And therefore, of course, their use, you can see here a picture, their use has to be carefully evaluated and managed. Indeed, there was also the problem of the price, but now the price of photovoltaic panels is decreased, is going to decrease, and therefore they are emerging as an important opportunity. On the other hand, affirming that the solar and wind energy, which actually cover about 1%, as we mentioned earlier, of the global energy usage, affirming that by 2050, solar and wind will cover a significant amount of our energy demands. Like sometimes some people say that they will be able to fully cover our demand, or significant percentages like 30%. It's a bit overstated because if now we are at the level of 1-2% of coverage of global energy, it's unlikely that we can exploit more solar and wind energy in a so relevant manner. And there will be an increase, but it is overly optimistic to state that these sources may cover a significant amount of the future energy. And this is demand. And this is something, it's a consideration that you have to keep in mind in view of finding a final conclusion of our discussion today. So basically, we have highlighted the importance of energy. We have importance of energy. We have highlighted the current incidence of renewable. We have highlighted the need and the benefit that can be obtained by converting to renewable energy. And also we have highlighted the costs and the opportunities for future expansion. And then we will need to find a conclusion. So what is the way forward? What is a reasonable way forward? But before then going to the conclusions, let me talk about nuclear energy, because this is really the missing piece. And let me just download the PowerPoint because this is updated. This is the missing piece, and it is extremely important. And on the other hand, it's something that has been long discussed, considered, implemented. So in order to understand what could be a future evolution and what could be a wise strategy for the future in terms of covering a significant amount of our energy needs with nuclear energy, we need to give more details. First of all, how it is generated, the nuclear energy today. It is generated by nuclear fission, and we will see details, which gives a lot of energy in terms of heat. And then the heat is used to generate water vapor that pushes, activate a turbine that generates electricity. This is the way is produced. How many we already learned what is the percentage of global demand that is covered by nuclear energy. Is not large, it's about 5%, and it's about 1/3 of the electricity. 1/3, if I remember, yeah, a little bit less than 30%. From Wikipedia, as of September 2023, the International Atomic Energy Agency reported that there were 410 nuclear power reactors in operation in 32 countries around the world, and 57 nuclear power reactors under construction. What is the history of nuclear energy? Let me go back to figure here. What is the history? Okay, first of all, the start of the nuclear age dates back to, as you may know, to the Second World War, after the work of Enrico Fermi. And then after the first usage of nuclear energy for military purposes, then the usage of nuclear energy to generate electricity became a reality. But as soon as it became a reality, important concerns were raised about the safety. And these concerns, unfortunately, were also motivated by the occurrence of two accidents. The first one occurred in 1979 in the United States, in Pennsylvania. And what happened was that the reactor, which we will learn how it works, the reactor basically has to be controlled, because the nuclear fission is a process that is reinforced by itself. So when we basically provoke the fission of a nucleus of an atom, then there are several particles that protons and neutrons that are released, which can collide with other atoms and therefore perpetuate this fission. So it has to be controlled. It has to be controlled because otherwise the temperature of the reactor increases, and then it can fuse the container, and then these particles can spread into the surroundings, and we know that they are lethal for the human health. And also their decay, their radioactive decay is very slow, and they can travel for long distances, by the way. So what happened in Pennsylvania in 1979 was a malfunction at a cooling system, and this caused the reactor to shut down automatically as designed. Okay. However, there was a valve in the primary system that became stuck open in the primary cooling system. Operators mistakenly believed the valve was closed due to misleading instrument readings, and the result, the liquid that was used to cool escaped. Okay, and therefore they believed the valve was closed, the valve remained open, and then this led to a loss of cooling in the reactor core, and the core temperature rose, causing a partial meltdown of the nuclear fuel. So there was a human error, and which is believed to be caused by inadequate training of the personnel. There were no immediate deaths or confirmed long-term health effect directly linked to the accident. So it was an accident with a relatively minor consequence, but however, it caused a public fear and a loss of trust in the nuclear power. And it led to major changes in reactor safety and in operator training, but actually it caused a slowdown in the development of nuclear power. And then there was the Chernobyl disaster occurring only 7 years later, and this one, unfortunately, was much more a disaster of that. What happened is that there was a late night safety test intended to simulate a power outage, and the operator then disabled several critical safety systems to carry out the test. Okay, and the reactor was operated at an unstable low power level. And this condition increased the reactor's reactivity due to its design characteristics. And then a sudden power surge occurred when the control rods were reinserted. And the surge caused a rapid increase in the heat and pressure within the core. And then this led to a steam explosion that destroyed the reactor vessel. And the second explosion exposed the reactor core to the atmosphere. And then there was a fire that was triggered by the graphite that is used in the reactor. And then large quantities of radioactive material were released into the environment. There is a Wikipedia page on this disaster if you want to get more details. They are, of course, accessible to the extent we know them. And unfortunately, this radioactive plume was spread over a large part of Europe, and also in Italy. I well remember there was a concern for this radioactivity that was measured as increasing. And unfortunately, there were several deaths, immediate deaths for workers within a few weeks, and other thousands suffer long-term health effects. As a consequence, there was another slowdown of the popularity of nuclear power. In Italy, a referendum was called in, I think it was 1980, where the majority of the people voted against the nuclear power plants, and as a result, the few power plants that were operating in Italy were shut down. And this is the reason why there was a lot of concern regarding the nuclear power. And this is why the production of nuclear generated electricity slowed down. Now, how does a reactor works? And let's concentrate on the nuclear fission first. And let me see the figure. Okay, here is an animated figure of a reactor. Basically, you have the vessel. It is the reactor itself where there is the nuclear fuel, where the fission is triggered. I'll give more details in a moment about what fission means. And there are control rods, which are used in order to control the subsequent multiplication of fissions, to keep these fissions at a level that is stable and controlled. And then there is cooling liquid, a cooling fluid in red that goes into the vessel. It's pumped by a pump, is pressurized by a pressurizer, and also the cooling liquid, the cooling fluid, allows to control the dynamics of the reactor. We need this cooling fluid. Then the cooling fluid is, of course, when it comes out from the reactor, is very hot. And then it flows back into a steam generator, inside the steam generator, where there is water that is getting into the generator, cold water getting into the generator that evaporates, generates steam, and this steam actuates a turbine, and then the steam goes into a condenser, which is kept cold by another cooling fluid, and then there is the generation. This is a detailed picture. Here below you have a more schematic picture where the vessel and the steam generator are schematized in a unique container. Actually, they are often separated, but the moral of the story is the same. You have generation of power that goes into the turbine, and then it is condensed and goes back to the vessel in this scheme to keep it cool it down. This is how it works. So what is the fission? The fission, there are details here, is a particular disintegration process during which heavy nuclei, so not in the not any nucleus, but heavy nuclei, such as those of uranium or thorium, if suitably bombarded with neutrons, split into two fragments, both positively charged, which violently repel each other. So they basically it's like an explosion, and move away each other with high energy kinetics. This is the generation of energy. The split implies a move away of these two parts with a lot of kinetic energy, and neutrons are also released during fission, and which in turn, these neutrons can induce other fissions, and this is the multiplication, okay? And it's a so-called chain reaction. Very good. Now, what is nuclear fusion? This is the interesting story. It's another way of getting energy from nucleus of atoms, of suitable atoms. And it is the nuclear reaction that occurs in the stars with the production of an enormous quantity of energy. And it doesn't produce any lethal radiation. And that makes it very interesting, because it doesn't imply the production of radioactive material. It doesn't imply the production of scores, because there is also the garbage resulting from this, from the nuclear fission. We have the problem to store it. So currently it's stored in deposit in the underground, waiting for its decay, but the decay is very low. The nuclear fusion doesn't have this implication, so it's a much cleaner way of producing nuclear energy. And it works with two nuclei of light elements, such as deuterium and tritium, and they are fused to form a nuclei of heavier elements, such as helium, with an emission of large quantities of energy. So it starts from light atoms, which are fused to generate a nucleus of heavier elements. The problem is that the two nuclei can fuse only if they are very close. So they need basically, they need to be in a way put very close together, and we need a very high temperature to fuse them. And because they need to collide with a very high kinetic energy. And the temperature is indeed very high, because in the lab to obtain a fusion, we need a temperature of about 100 million degrees. And this is the problem. And it has to be kept for very long times. Keep in mind that the internal temperature of the sun is estimated in about 14 millions of degrees. And, but in the sun, there is also a lot of compression. Why? Because the sun has a very large gravity. It's the gravity of the sun makes this light nucleus very close. They compress each other. So from the operational point of view, production of large amounts of energy through nuclear fusion is still a problem. We can work with it in the lab, and but we are not still able to work at an industrial scale to produce it, produce this kind of nuclear fusion energy for civil use. And the European roadmaps towards fusion electricity envisage the construction of the first reactor that feeds electricity into the grid electricity network, after 2050. So what is the conclusion of the story? The conclusion of the story of nuclear energy is that probably by 50 years from now, hopefully less, we were able we will be able to generate nuclear energy through nuclear fusion. This would open new doors because it is a clean energy, it's not dangerous, it's sustainable. Currently, we cannot rely on it, but maybe that in 50 years we can. And therefore, the question is it reasonable now to accelerate our timeline to achieve by 2050 carbon neutrality with high social cost and with question marks about its feasibility? Or is it better to push on the development of nuclear plants and the development of our technical capability of using nuclear fusion with a target that is a bit longer, but of course could radically change the picture? The problem is that we have also to work with the attitude of the public to accept it. And we also have to, make a kind of strategic prediction of what will be the evolution of the science, of the technical knowledge, in order to make a reliable prediction of when we will be able to use this kind of energy. And there is also a political evaluation that has to be made about the strategy that we should follow. So, of course, this is a question for experts. And if you listen to the experts, and I'm not an expert in energy production, and if you listen to the experts, they have different opinions. Like for any question related to science, our scientific development, and therefore it is difficult to reach a conclusion between ourselves. I can tell you my opinion. I am convinced that the target of decarbonization can be reached only if we if we remove our concerns related to the nuclear energy. And keep in mind, when there was the referendum in 1980, I voted against nuclear energy because I was convinced that it was too dangerous, and I also was convinced that it was something not environmentally friendly. But because of the risks, but also because of the problem of the scores, etc. But now, if I look at the picture, again, I'm not an expert, but if I look at the picture that I tried to explain to you today, I see, I tend to believe that it's not feasible to reach carbon neutrality without relying on an expansion of the nuclear energy production. Now it's 5%. I think it is unreasonable to think that, to assume that solar and wind energy will get to the target of covering 1/3 of our energy demand. Now it's 1%. So I think it can get to, let's be optimistic, 10%, but not more than that. So it means, according to my interpretation, that nuclear energy from 5%, it's possible instead to increase to 30%, because, these plants, even if we now are forced to rely on fission, these plants are now more safer than in the past. If we look at, for instance, artificial reservoirs, at the beginning we had several disasters for dam break, and recently no more disasters because, of course, we learned. And I think also for nuclear plants, I think that in the meanwhile, while we wait for nuclear fusion to become available, I think that we have to in a way, remove some of our reservations against nuclear fission. So promote an amplification of nuclear energy while we wait for nuclear fission. Why nuclear fission is needed? I think it is needed because it's definitely safer and there is no problems with the the garbage with the scores, and with the remaining, I don't know how to say in English, scores is not correct, but anyway, I think you understood. And the byproduct of nuclear fission. Now it's a problem, but of course, it would be a problem to assume that forever we can rely on it because of the problem of the byproducts. But on the other hand, I think it is reasonable, according to the opinion of experts, to assume that if not by 2050, by 2100, we will be able to use nuclear fission at large scale. So I think this is the way to follow, which will also allow us to avoid the environmental impact of promoting, of expanding too much solar energy generation and wind energy generation. So I think this is probably the way to follow. So it is something that you can very often list at the center of the debate among politicians, like what should we do with nuclear energy? I think that probably instead of going back to a massive use of fossil fuels, like some of the superpowers now are considering, I think that probably the nuclear energy, I changed my mind, is probably the solution that we need to adopt. But in any case, I want to stress once again that this is my interpretation. It's an open challenge, and of course, we cannot have the ambition of answering global challenges within this room. But on the other hand, I hope that with this introduction, I gave you some information in order to reach a better understanding. Going back to your question, what should we learn? What should we learn here? I think look at the big picture. So forms of energy, we consider two classifications. Try to get expert about these two classifications. So just want to remind you, the first one is this one, okay, this figure here, and the second one is this figure here. So focus on these two figures, and then focus on the big numbers. So what is the main source of emissions in a question that you could get into a quiz is what is the main source of emissions, of CO2 emissions at the global level? And you may have three answers: energy, industry, waste, agriculture. Okay, just remember that energy is the largest. You don't need to remember 73.2%. Okay, and same here, world energy balance. I mean, what is the incidence of fossil fuels? You may get a question like this: 10%, 20%, 50%, more than 80%. Usually this is the type of questions that you may get. So I think I stressed a lot that fossil fuels are covering more than 80%. So this is the message that you have to get. And I wouldn't say anything here. So, I mean, you may get in a quiz, or if the quiz is 30 questions, it means that we prepare about 90 questions to be extracted by chance for each of you. In these 90 questions, there might be like 5, 8 questions on energy. Okay, this is to give you an order of magnitude. And other things could be related, other questions could be related to renewable energy, and the question may be simply what kind of what are the energy sources renewable in this list? And there is a list, and then there is a multiple answer question, which you have to identify what is the right one. So, I mean, it's not really a demanding question. And then for nuclear fusion, nuclear fission, you may get a question like, what is the kind of nuclear reaction that is implying the emission of radiations that are dangerous for the human health? Nuclear fusion, nuclear fission, just to be clear. I think that's it for me. And yeah, I forgot to say one thing, and which is placed at the end of the lecture. So, and this is really a small addition, because there is an increasing popularity of nexuses, okay, which mean a nexus means an interaction of several components of our societal organization. And these nexus, why they are increasingly popular? Because they allow to highlight the feedback in the Earth system and in our societal system that can reinforce each other and allow to see what is the importance of connections between different subsystems. And a nexus that became very important, and you can look at Wikipedia and whatever, it's the water energy food nexus, because food production is tightly related to energy production, because we mentioned that food production needs energy, but also food production is related to water for obvious reasons. Irrigation is the major consumption of water by humans. Water and energy in turn are strictly related by several links, because hydropower and energy from the sun and is used also to mobilize to evaporate water, and also water is used in the cooling systems of nuclear plants and in the cooling systems of thermoelectric generation. So there is indeed a very tight relationship, and so there are several connections in this system, which is depicted here. And indeed, the solution of the management, this implies that the management has to be devised by looking at all these connections. And the solutions are to be sought by involving the stakeholders in that. And therefore, this is why this nexus becomes so important, because it's important to raise the knowledge of people and the sensitivity of people to gaining a better understanding of these connections in order to support rather than preventing efficient management. And that's it. There is nothing that you have to learn about this. It's just an example that I wanted to make, because there are several other nexus that are being developed, proposed, and which represent a kind of attempt to raise, as I said, the attention of the public to reach a better understanding of the coupled environmental societal system. That's it. Do you have any questions? Okay, thank you very much. I am stopping the registration, and I'll make available the video soon. Thanks.